Today we're going to try and approach the questions on capacitance. So we're given a coaxial cable of length L, as denoted here in the drawing of a cylindrical inner conductor with a bunch of other data. But let's get started with a small picture. So I denoted the coaxial cable on the z-axis. Now notice that you can draw this on any axis. I just denoted the z-axis as my preference. But as such, I will move on. Now, I did draw also a top view here. So as we can see, there is a certain dielectric constant between radius A here and radius B. And there's also another dielectric constant between radius B and radius C. Okay, now I will assume a biasing of this sort here. So that means that we will have a Q plus positive inside here and a Q negative on the outside. Notice again that I can assume the biasing of my choosing. I just noted that way because I do want to work with positive inside. Now let's move on to the boundary condition. Now as we can see here, I just took in a zoomed in approach and just donated it and just drew it on here. So the electric field from the biasing that we just assumed would go from the left here to the right based on this drawing. So that means that all of the electric field will be due normal to the boundary. Now notice that this is a known case on the boundary, and that is the dielectric constant times the normal component of the electric field is equal to the same thing on the other side. That also means that the electric flux density will also be equal on both sides, which means we can just donate it as electric flux density without subscript. Moving on, that means I can draw a simple drawing where the electric flux density is just moving, it's of the same magnitude or the same magnitude throughout the drawing here based on the biasing that we assumed on the beginning. The direction will be radially outwards from the center. Or in this case, the radial is donated in cylindrical coordinate as rho. Okay, now here we're just doing Gauss's law. So this closed surface that I chose would just be a simple cylindrical Gaussian surface around the cylinder that you see in that drawing here. So that means that I will have D, which we just donated is the same throughout here, times the Gaussian surface. Now note that mathematically you can see that the only side that will be considered is the side. But if we just do a quick mental check, we can note that because the electric flux is radially outwards, it will only be 90-degree orthogonal to the sides, and it will not pass through the top or bottom of the cylinder. So that is clearly seen that these will be 0. As such, after manipulation, you can find that the electric field is equal to that formula here. Next, we move on to figure out the voltage. Now, this seems quite complicated, but it is quite simple. So notice that we are just plugging into electric field that we just determined above times the DL. Now, the DL, you can either understand it or you can just pull it up from the formula sheet. And as such, you can notice that the phi and the z components, at least in the cylindrical coordinate, will be 0 just due to the dot product as you see in the next step here. Now moving on, you notice that the dielectric constant is not the same for both cases, so you have to take that in consideration and separate them. After doing that, you can manipulate to get Q or to get this formula here, and that will be equal to your voltage. Moving on, we can just plug it into our C equals Q over V formula, and we just determine V in the step above. Now we can see that the Q's cancel out, and we can notice that we will be left with this formula here. Now, as a quick check, we know that the capacitance should be positive, noting both of these would always be positive and all of the other values are positive. Our answer should be correct. Thank you.